Okay, let's start the next talk by Asashiba Sensei, Professor Asashiba. And he's going to talk about relative co-resolutions and relative weight numbers. So please start.
Can you hear? 聞こえますか？聞こえるみたいですね。はい。So relative co-resolutions. Usually, the name Koshul is known as Koshul complex. So Koshul co-resolution is defined here. Okay. Now it is already published in Journal Pure and Applied Algebra 229. So now I will go. First, I want to talk about introduction. So I first fix notation. Oh, notation disappeared. Why? I collected notation here, but disappeared. Strange. Anyway, I hope everything is kept otherwise. Okay, now, so now it is disappeared. So I will write here A is the finite dimensional algebra with orthogonal set of primitive idempotencies P. So here E. Orthogonal set of primitive idempotencies. Usually basic, and then now I fix K field. This is over K, and here model A is the category of light modules. Maybe that's all of them. Model A opposite is the category of left modules, and then GB module here, right module, and then endomorphism algebra of G is denoted by lambda here. And then G is generator. It is called the generator. Generator, mod A. The algebra A itself is contained as a direct sum of G. And the co-generator, if the dual of A dual of A, right module is contained as a direct sum of G. I hope that's all. Okay, now from here. And now I let PAI, this one more. P is a finite concept. With elements 1A up to 1, say, P. Okay. Then usually it's instance algebra, what it is called later. I'm sorry, some pages deleted. Okay, then now I want to first review the definition of bit numbers and relative bit numbers. Yes, and further, I put I to be the additive closure of the module G. It is a full subcategory of module A, such that is a direct sum and over some modules, copies of G or some. And then I fix this I additive subcategory closed under direct sum and indirect sum, finite direct sums to be I here. Okay, now then projectively decomposables EIA is denoted by PAI for all elements of AI。持ちましょう。はい。はい、これで聞こえますか？ありがとうございます。Then, what is the bitch number? If we make a minimal projective resolution of M in this way, then they are determined by M uniquely, and then decompose it by as a direct sum of indecomposable projectives, and then the multiplicity here, beta MIA, is called the ith pitch number of M at the vertex A. And then this is the original pitch number, and then the relative version is defined as follows. And now I resolution of M is determined by using modules in I instead of projective modules. Later I will explain more precisely. And then analogous to a minimal projective resolution, a minimal I resolution of M is defined. This have this one. Sorry, I have to add. So G is the direct sum of VI's, and I is I in I, a subset. And I and J are not equal, then VI is not isomorphic to VJ, and they are indecomposables. Indecomposable decomposition, and only finitely many. Then the project, all modules in I has the form of this finite direct sum of this form. So then, if this is a minimal I resolution of M, then these numbers are determined by M uniquely, and this number is called the I relative ith pitch number of M at I. So now this is just a review of the definition. And then my talk is heavily started from reading their paper, CGRST, 5 people, by 5 people. And so Chachusky and others gave an efficient way to compute I relative bit numbers. This was the original title of their paper. For modules over A by using the so-called Cauchy complex of KL modules for lower they used upper semilattice, but here I'm talking about right modules. Right modules are contravariant factors, so all story changes to opposite side. So in their case, it was upper semilattice, but in my talk, lower semilattice. And then, so I have to review what Cauchy complex is. So now let L be a finite poset and B to be the poset incidence algebra of Li. I made a definition of this, but it disappeared. I'm sorry. So an EA, the idempotent corresponding to the number and element A. And then, so here, L can be seen as given as a quiver with relations, and whose quiver is given by Hasse quiver of B. And their vertices just the same as the element of L. So now indecomposable A modules are now BEA, EAB. Right M B modules. Indecomposable projective has this one. And then, so now, this is important notation. And for each A in L, the cover of A is a predecessor of A, such that in between A and B, nothing is included. And assume that L is, as before, lower similattice. Then this guarantees the following. For any A in L, a non-empty subset of cover A, And if S has upper bound, then it has the join, so least upper bound. And then we denote here join of S to be A if S is empty. So look at this image. So we have A element of L, and then they are direct predecessors, and choose some subset S here. And then if S has upper no-empty upper bound, then it has the least element. So this is guaranteed by lower similatris. Their assumption is that for this assumption, no need to assume the lower similatris. But for make it easy, I assume this property. Then the Cauchy complex KAM down over module M, B module M at A is defined as a complex of this form, here K0, K1, up to K something, and where each term is a vector space. And so here, if K0, zero case, it is just a MEA. It is as a representation of, of P, it is usually written by MA. This is usually MA1, MA, sorry. But we are dealing with now right B module. So from the right, we can multiply the idempotent EA to have this vector space. And then for I bigger than or equal to 1, it is the direct sum of those things. Where here, so this S, it is difficult to see here AI, where AI is a subset of cover A, such that the number of elements is I, and S has with the assumption that S has an upper bound. So then, and here for those S, we can by this assumption we have a join of S, and then the join of S is an element of L, and so then some idempotent is corresponding. And then we make this vector space. It is usually denoted by this as a representation of quiver. So each term is defined in this way. They are direct sum of some ME something. And then this is complex. So then we have to define differential. And so here, differential from I to I minus 1. So they are direct sum of vector spaces, and so it is possible to give it as a matrix in this way. So here, this consists of 1, 2, 3 things. And the first one is easy, and this is 0 or 1 was 0. If it is 1 if T is a subset of S, otherwise 0. And then a non-zero element assume that T is a subset of T. And then the cardinality of S is I, and cardinality of T is Ti minus 1. So one element missing from S. So then T, if S is this one, then T doesn't have one element of S. So now we have here AS0, AS1 up to here, and then so here, so S0, S1 up to, yeah, we have this order. And then count the missing element ASJ from the beginning by 0, 1 up to J. So take this J, and then this is called NSD. Okay, so this is a alternative, kind of alternate sum. And then this is just a multiplication by element of B. Here it is disappeared, but this means as a poset S, and so L is regarded as a category, and then we have unique morphism from A to B. If A is less than or equal to B, it is denoted by PBA from right to left. And then this is element of instance algebra L, namely B. So, and then row means right multiplication by the element of B. So then, because S includes T, then the upper bounds has the converse relation that upper bound of S is included in upper bound of T. Then the taking least elements, conversely again, join of S is bigger than or equal to join of T. And then, because we are dealing with covariant factor, namely right module, so then this goes to this, but then the converse means like this. So then from here to here, we have a morphism, right multiplication. So in this way, each component, MES, MEVT, it is defined by the right multiplication of this element of B. So in this way, we can define this entry and then make the matrix to define this morphism. So this is the basic definition of causal complex, and then it is defined automatically in this way. And then looking at the paper, I wrote it as a theorem, but they write it as an observation. It was not so difficult, but this is very important that this Betti number, usual Betti number, can be computed as a ith homology of this causal complex by calculating its dimension. So this is the central starting point of my talk today. So now their idea was to use this fact. So their idea. So in their paper, they have bimodule, BA bimodule in algebraic sense. They didn't say so, but this is the same. They define some BA bimodule and then consider a joint pair by tensoring and Hom. Usual Hom tensor are joint with the correspondence projective resolution left-hand side correspond to I relative resolution on the right-hand side in mind, and then apply this theorem to have relative bit numbers, theorem for relative bit numbers. This was their idea, but instead here, I posed the following problem. So this is construct the same tool in model A itself, namely for algebra A and the M module A module, and fix finitely many indecomposable modules, and I to be additive closure of the direct sum of them. Then define. Is it possible to define some similar KIM down such that its dimensional ith homology gives us the this number, Betti number, relative Betti number. And then relating this story, I call this KIM down to be causal complex of M at I. Okay, so then I want to find a similar complex which has the same property like this inside module category of A. So now I now first sketch the solution, our solution. Now, for A, so this is a key point, and we take instead of M. So Km was defined here as a complex, here MM. So change M to be B. B is a instance algebra of L. So change B here. M changed to B. B is a BB bimodule. The structure of left B module is essential now here. Now replace M by B, then we have this one and this one. As you see, this is left B module, left B module now. And then proposition. So then this KAB down is a projective resolution of simple left B module here. Simple left B module corresponding to the vertex A. So this is BEA over radical BEA. So this observation is crucial. And then this complex gives the same this desired property. And then looking at this, let's think of the following notion: formal quotient co-resolution here. It is a co-resolution in projective modules B, finitely generated projective module B, such that the definition is almost the same as you see, but on the left, not on the right. And then, so this is the same, and this is the same as before. The cover of cardinality I is taken as a join, and then multiply from the left, not on the right. And then it becomes conversely, last time it was from S to T, but now we have from T to S. By the same matrix, but here left multiplication, because this is a right module. Then we can multiply from the left here. So now this is left module. So sorry, left and right both appears in my talk. Here, this is now right module, the same side as M, the same side as M. And then this C is living in the right module world. It is their projectives. And then, as easily say, the following hold. Okay, so now this BI, KAB, which was defined before, is just a B dual of the CA. Just a B dual, because you see, this is here from the right, but it was from the left. Okay, now, and then further, this KA M can be obtained by taking a home space of this form, C down A on M, right? And then because C is this form, if we take home CM, then we have MA here. MA here, right? To have them, we use this formal direct sums like this and take home. Then we can obtain this quotient complex. So then this is the idea. So then inspired by this fact, we define an I relative co-resolution y up or Vi as a co-complex corresponding to this C up, and consider the adjoint pair between mod A and mod lambda. Lambda is the endomorphism algebra of G, given by the bimodule G. So here, G was originally right A module, and its endomorphism algebra is lambda. So G is a lambda A bimodule as well. So then this bimodule gives us this easy adjoint pair. And then we define this one. So after defining this one, and then G dual, taking G dual y down, this should correspond to this one. Is a projective resolution of left lambda module as before. Then we guess that the home y up with M, this one, will give us the desired module, a desired complex. Okay, so this is the plan, how to solve it. Now, I will now go to in detail. 14, okay. So now I have to define a review I relative homology. So now first, so say let x, y, and x be any module, and f to be morphism from x to m. So then m, this f is called right minimal if for any endomorphism from x to x, if h has the property that f is equal to hf, then xh should be automorphism. This is stated in a different way, but today I have no time. Just this is usual definition. So right minimality is corresponding to projective cover. Okay, then instead of having projective cover, we use this notion, right eye approximation of M. And then so this this F is called right eye approximation. Right eye, so M is on the right. Right eye approximation if this X is in also I, and whenever we have a morphism from an object Z in I to M, it always factors through F. This is the condition. Namely, it is possible to write in this way, home Z blank sends this to an epimorphism for any G in here, something H here, and then it is mapped to here. So this property is stated in this way. It is an epimorphism. And then if G is a generator, note that if G is a generator, then this F is automatically become epimorphism again. Because G is a generator, so then we have some epimorphism from the object Y. A to the N is in I, and here epimorphism. So then factor through epi factor through this one means that F is epimorphism. And then if F satisfies both of them, right minimal and right eye approximation, then it is called minimal right eye approximation of I. And dually, left minimal left eye approximation and the minimal left eye approximation is defined. So then now this is a definition of the eye resolution. So first, one step is defined. So then using, so we have epimorphism from projective to any morphism, then we can form projective resolution in the same way. We define eye resolution here. So eye resolution is a sequence in this form, ending MM, such that, so here, this F0 is a right approximation. And then take, this is the same, and take its kernel, and then construct again a right approximation, and so on, to have this sequence. So then this is complex. And if G is a generator, then this becomes an epimorphism. So this sequence becomes an exact sequence. But usually, in general, not. And then a minimal sequences take each step minimal left right approximation. In that case, it is called minimal eye resolution. So then, the similar as before, if we have a minimal eye resolution, it is uniquely determined by M. And here, because we are assume that G is only, we are taking about only finite many VIs. So namely, G is a finite dimensional one. So then always this eye approximation is existing. This is all, they exist. They exist. And then by Krishna's theorem, each term can be written as a direct sum of indecomposable objects, and then the multiplicity is uniquely defined. So these multiplicity is called I relative ith Betti number. So now I put I relative here. So then then if Z is object Y, then by definition, this home functor sends high resolution to exact sequences because here we have epimorphism. So then this becomes exact. Okay, now definition dually, we define I co-resolution or minimal I co-resolution by taking co-kernel. And then similarly, minimality, in minimal case, the multiplicity is uniquely determined and it is called co-Betti number. Okay, so then, so I want to give now a Cauchy definition of Cauchy resolution. So now, or to fix some element I, and then denote by EI the idempotency corresponding to VI. G is a direct sum of VIs, and then projection and inclusion. So this gives us an idempotent of lambda. So this is corresponding to VI. And then, so now I want to skip this, but radical map is okay. Okay, so now thinking about radical lambda, and then this home set is VIG can be seen regarded as lambda EI, a projective indecomposable lambda module. And as before, we can define simple module, lambda module by using EI. Okay, then definition. So this is the definition of I-relative Cauchy complex. This is constructed as follows. An I-relative Cauchy complex Y up of BI is a co-complex of this form where we have the following commutative diagram. At first, so this is our sequence. So first, D0, this is the most complicated part. The easiest one is just the identity. So here, this is very general. At first, we take left almost split morphism, nu zero here. And then after that, the same, we take minimal left approximation here. And then take composition. And then the condition of D0 is just the existence of these morphisms satisfy making these triangles commutative. So this means this is said to be that D0 is equivalent to this eta. So eta is the essential part, and we can change eta loosely by these existence of morphisms. And then the other is simple. So take cokernel of D0, and then again left approximation, and then composite to have this D1, and then again cokernel, and then left approximation, and so on. So these red arrows are constructed as by taking left approximation, and only this is left almost split map. This is sometimes called source map. So this is the definition of I-relative Cauchy complex co-resolution. And later, if I have time, I will show example. So now minimal resolution, co-resolution is I-relative Cauchy co-resolution where D0 and G1 also, they are minimal. This. And but notice that even if they are minimal left minimal, but this cannot be left minimal sometimes. And so even if we have this identity, so D0 equals to eta case, we can't assume that this is minimal, even if we take this, they are minimal, but this cannot be minimal. So I call it pre-minimal if these things are minimal. So a little different, minimal and pre-minimal. And then this is easier to compute. But as we see, we don't need to take care of a minimality. So then that's enough to think in general this iterative Cauchy complex, a co-resolution. So then this is a theorem. So now let A M be an A module and Y up and sorry, it is Y up and I will Cauchy correlation VI, then the following hold. So now a G dual of Y up gives a projective resolution of simple left lambda module SI. So this is important. So then because of this, two holds, namely for each non-negative integer I, we have the relative Betty number is really computed as a dimension of ith homology of this home space. So this is just an abbreviation of home. This is just the home, abbreviated. And then this is important to compute left-hand side. Y need not to be minimal. Any resolution, such resolution can be used to compute relative Betty number. But to define Betty number, we need minimality. Minimal I resolution is needed. But to compute it, Y need not to be minimal. So then, so this gives a problem. Namely, we can take this Cauchy complex to be the M dual of Y up here. So this gives us a problem, answer to the problem. Okay, now as a corollary, it is possible to characterize when M is in I. And usually as an application, I take G to be a direct sum of all interval modules. And then in that case, I becomes interval decomposable modules. So this means this gives us the criterion when the given module is interval decomposable. This is given by H1 is 0, or dimension is computed by computing dimension multiplied by dimension Vi, or in that case, M is of course decomposed as a interval module and with multiplicity given by dimension of homology. Okay, so this is easy corollary. And then to compute this one, H1, H0 is here, here. Only we need to have compute left almost split map and left IO approximation. And then this is already known how to compute. And then later for the interval case, I will further give some information how to compute left eye approximation. And then in that case, zeroth Betty number is just a difference of these two dimensions. So now application. So now main application is for interval case. So now let P be a finite poset and A to be instance algebra of P, and I the set of intervals. So the interval means convex and connected both are poset of P. And Vi, the interval module for I, namely, so this is as a representation of Hasekivo P. So at each vertex, it is put K or 0. If X is in I, then it is K, otherwise 0. And if both X and Y are I in I, then the morphism from X to Y is put to identity, otherwise 0. So the very easy, simple module defined by I. And then take G to be the direct sum of all interval modules. And then in this case, as I said, I is said to be interval decomposable modules in I is set called interval decomposable. And I approximation is now interval approximation, I call. Instead of I write interval. So now, for example, P, let P be a finite poset, something like this. 4 times 2, two-dimensional grid. And for example, this is an interval of P. And then interval module BI is given as before. So K, 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 and identity, and other one as 0. So this is an interval module. And we inside I, we have some subset. And such, for example, this one. This is closed and taking predecessor. It is called upset. And this is closed and predecessor. So this is predecessor postconjuncted. Yeah. Then this kind of subset is called downset in I. So this is used. And then lemma. And this is very important. For any interval I and for any submodule S of Vi, we have the factor module Vi over S, and S itself is in interval decomposable. So all indecomposable Vi have this property. Then by using this, the following theorem follows. First I will explain this. For any A module M, M has a minimal interval resolution of finite length, namely for some R, R plus 1 is 0. So this means all x M with R plus 1 is 0 in that case. So this is sometimes called a global dimension, interval dimension of A is finite. Okay, and then remaining one is like as follows. As if we have Ij, an interval, and then there exists some monomorphism from Vi to Vj if and only if I is an upset in J. Dually, if there is an epimorphism from Vj to Vi, if and only if I is a downset in J. So then notation, we collect all monomorphism of homomorphism from XY and denote it by mono XY. And if it is epimorphism, then epi XY. So then definition, S int and F int. S int is just intervals I such that there exists monomorphism from Vi to M, Vi to monomorphism M. In such case, I is collected here, submodule S. And F int is conversely, if there is an epimorphism from M to Vi, then we collect such I to form F int M. And then we define for example here, Vi, Vj here, no. I less than or equal to J with respect to a submodule is defined to be first in here. So this means I is upset of in J, and for any monomorphism Vi to monomorphism, and then there exists some Vj monomorphism such that this is extended to here. In that case, we denote this by this, and dually F, and then collect such maximal element to denote the set of them, max S int and max F int. So then the following gives a way to compute relative, right approximation or left approximation. So now let f from x to y m be a morphism in module category A with x I, namely interval decomposable. Then the following are equivalent. So f is right interval approximation if and only if for any monomorphism here for any I. So this means there exists a monomorphism from Vi to M. So take any such I, then take any monomorphism here. Then this G factors through F. This is a proposition, property 2. And similarly, we will make the set smaller. So smaller set max S int. For this, the same holds, is enough. So then to test that given f is right interval or not, we just test it by using monomorphism from Vi, where I is S int, or max S int. And then this, so okay, this is okay. And 1 to 2 by lemma above. 1 to 2 is given by this property very easily. And then 2 and 3 is almost trivial. 2 to 3 is trivial. And 3 to 2 is again very trivial. Because for any G, so if we assume 3, then 2 holds, because for any G monomorphism, there is something which extends to here. And then by condition 3, it is factors of F. So then we have this is equal to this. Okay. And then so now a similar argument was used by Aoki Esclatada. They gave a necessary condition for minimal right interval approximation with a similar argument. And dually, for the left interval approximation, we have this similar composite proposition. So then, by as a corollary, we have the following. This is again a characterization of interval decomposable module here. So M is interval decomposable if and only if it has decomposed as this form. One dimension is equal to given by batch number on this one. And then not only S int, it is possible to write it as using F int, but co-batch number. And then the similar one. And then if M is interval decomposable, then M is decomposed as in this form where I is both in S int and F int. So in this way, the scope of intervals become very small. Then for 1 to 4, we have the similar one, but here both S int and F int. Yes, but it's okay. And then in particular, this is true. If Vi is a direct summand of M, so Vi appears in this decomposition, then I is in both max S int and max F int. So this set is much smaller than the interval or S int, so smaller one. So it's enough to check whether Vi is a direct summand of M by only these sets. Okay, then corollary. Another one is using, yes. So then, but here, as you see here, beta 0 appears here, and the beta 0 can be computed by using Cauchy complex. So then we can replace it by dimensional homology of this complex to have this equality, for example. Of course, other case too, this case or other dual case. And then this was used to apply the following compression multiplicity, computation this multiplicity. So that I want to review this first. So now we keep the setting in section 4 and let M be an M module and R the length of the minimal interval resolution. By theorem, it is known to be finite. And in the following special case, unfortunately, at this moment, only the following special case, we have the following result. The coefficients of interval replacement delta xi m over m can be computed by the interval bit numbers of m. And here, interval bit number is related to interval approximation. Then this means that interval replacement, this is given by Möbius inversion of some multiplicity. Later I will explain. These two kinds of approximations are connected to each other in this case. Okay, so here this is interval replacement. So whose coefficients are given in this way here. So these are Möbius inversions. For example, so this setting. So this the next theorem is dealing with this setting. So very special here, just a ladder case, Gn2, n times 2. So here, like this form. And then think the following poset morphism. So take this poset. This is a Hasse diagram of the poset, type A5, zigzag, and then define the poset morphism by sending these M shape to this M shape. So this is I. I is an I interval. All intervals of this commutative ladder have this form, or this or this. And then define, in any case, such Ci. And then let this is a poset morphism, then we can have an extension of here. In this case, unfortunately, I wanted to unify all stories by using algebra, unfortunately, but here this is a category. No, in this category, okay, it is okay. Okay, instance algebras, yes. So, okay, between poset, uniquely, this map is uniquely extended to algebra map or functor, K functor. And then, because we have this Xi, then Xi induces restriction functor from model A to Kp, because yes, M or a module is nothing but A to mod K functor M. And then we have here restriction, KQ prime. So then this is sent to this component to have a restriction functor. So then all module, A modules are sent to KQ prime module. It is very easy, just a M shape, zigzag. And then define CMI to be the multiplicity of the RIVI in the indecomposable decomposition of RIM. This is denoted by D. And then we have the function from the set of all intervals to the real numbers by CM. So I is sent to this number. So then, because it is easily seen to be, it is an invertible element, and then we can have inverse one, and then inverse is given denoted by delta. So it is called a Möbius inversion of this function. So then, so this is then in this theorem, in our theorem, we show that these C and delta can be obtained by Betti numbers, relative Betti numbers here. This was the main one of the main theorems in this paper. And then, as you see here, Betti number appears here. Then we can replace it by dimension of homology like this. So this is one corollary. In this way, these numbers are computed by dimension of homology. So finally, example is example first. So 3 times 2 case. Then take I to be this one in this way. No, not this one. 1, 1, 1, 0, 0, 1 means this is dimension vector. So here, here, this one. This is I. And then take module M with dimension vector 1, 2, 1, 0, 1, 1. This is indecomposable. The structure is given in this way. Then at first, it is easy to compute left minimal almost split stick map. This is given from here to here, and then take compute left approximation. Then the left approximation is given by this one. And this is from the beginning interval module. So then this is the same identity here. And then G0 can be computed. And then as a composite, we can define D0 and then compute co-kernel here. And then co-kernel is from the beginning intervals. So then we can take this as Y2. So here V1, Vi, Y1, Y2, this one. This is example of interval Koshiro co-resolution. So then interval Koshiro complex is given by the M dual of here. So here M dual to have this one. And this is easy to see that this is one-dimensional and 0, 0. So then Betti number is here at 1, otherwise 0. Yeah, so this is easy case. And finally, if we come back to the lattice case, lower lattice case, then our construction gives the same Koshiro complex as before. So this is an example, and both here, this is example of a D4 case, and take Vi to be indecomposable module over this quiver algebra without simple modules 1, 3, 4. And then let J to be, I to be the additive closure of P. This is P, sorry, this is P. This is P, curly P. So this P is this one. And then this P becomes KL. P is this one. And then L has this form. So they are intervals, everything intervals, and these morphisms. This is L. In this case, I, if I is 1, 1, 1, 0, 1, 1, so this case, and then we compute both minimal I-relative Koshiro complex here, and then this is formal Koshiro complex here. And they coincide in this case as a complex. Okay, so thank you very much. I have 2 minutes. These 3 are references which I cited. Okay, thank you very much.